Moritz. I work for a company called Edgeless Systems. And we work with a technology called confidential computing and are on a mission to bridge the gap between cloud native, the cloud native world, and confidential computing. Who of you have heard of the term confidential computing, trusted execution environments before? A couple hands. And then who has actually used it? Nobody. It's great. I'm giving this talk, so maybe we can change this, and you get excited, and we'll get hands-on afterwards. So, what's the biggest roadblock for cloud adoption? Obviously, security. I mean, there might be a couple other reasons as well, but what we hear a lot is there are security, privacy, compliance, regulation concerns. People would like to move more workloads to the cloud, but can't or are hesitant to do so because of an uncertain world in the cloud. And now imagine there's a technology that could fundamentally change the playing field, enable a completely new way of using the cloud. So to illustrate this a bit more, the cloud today is some space with a lot of dependency components, actors, that feels very insecure in some way, some very, very uncertain. And now, confidential computing, the idea is essentially to create a carve-out, a completely isolated space in the secure environment that is completely verifiable and runtime encrypted, and where you could move your workloads and your data and process it there and be sure that nobody could peek inside or steal anything. And this enables quite a lot of new possibilities, and quite naturally people are excited about this. Protecting data in use is one of the missing pieces for end-to-end encryption. And to give you the full vision, the CTO of Microsoft Azure, Mark Russinovich, said at the OC3 conference that his vision is that confidential computing will not only be for those specific sensitive data workloads, it will be for computing in general in the cloud. And that we will see this as an expectation that data is always encrypted, even while it's in use. We see confidential computing offerings in the public cloud. All the big hyperscalers have them. We see the different hardware vendors provide their implementation, their solution for confidential computing, maybe Intel, AMD, or ARM. So it's available today. We can use it right now. And we're going to take a look at what is actually confidential computing and how can we bring it together with the cloud native world. So confidential computing, if we take a look at the usual stack in our cloud environment today, we have our applications, containers, and then we have some operating system, Kubernetes, your kernel, and below that, some hypervisor, and then the hardware level. And all of these layers essentially need to be trusted. They are part of what's so-called trusted computing base. Back in 2015, Intel released its first generation of a technology called Intel SGX Secure Guide Extension that programmatically allowed you to basically create a secure enclave on the application layer that is enforced by the CPU and isolated by the CPU, and where you could move code and data and process it there inside the secure enclave and be sure that nobody from the other components in your stack could peek inside or could modify the code. And you could define them by three properties that are equally important. The first is isolation. So it's completely isolated from the rest of the stack. It's runtime memory encrypted, so even if you would have direct access to the hardware, you could not leak the data from there. And you have what's called remote attestation. So you have a way of verifying that this secure enclave has integrity and is confidential from the outside before you provide your data to this application. This was Intel SGX back in 2015. 2 years later, roughly 2 years later, AMD followed up with their solution. That's called AMD SEV. It took a slightly different approach here. Instead of doing secure enclaves that are more or less process-based, they decided to go and take the VM level as their abstraction layer. So you could create entire isolated VMs. Pretty much everything stays the same, but you now have a guest kernel inside this secure space. That means you have a slightly larger TCB, more code in the secure space, but you have a more standardized interface. You could just use it, you could run your containers inside such a confidential VM like any other VM. You don't have to adapt anything. So it's more designed for like a lift and shift approach, but with a slightly larger TCB. And Intel has announced their follow-up to Intel SGX called TDX that is essentially equal to this confidential VM concept. And also ARM has a technology called ARM Realms that we hopefully see in hardware soon. So we have these two types of isolated environments, the process-based secure enclaves, and now the confidential VMs. So what can we use? What can we use this technology for? We now have those isolated, runtime encrypted, verifiable environments. And we see, essentially, you could group them in two types of applications. You can make existing workloads more secure compliant, move your workloads to the cloud, and process them in this secure space. This typically lift and shift. And on the other hand, you can build new types of applications that are enabled by confidential computing in the first place. New privacy-preserving concepts that weren't possible before. And to give you an idea, one example, that was a project we built together with Bosch. The idea was that you have a privacy-preserving AI training pipeline for their driver assistance systems. So you have the car fleet, they collect a bunch of images where you have personal identifying information like faces, license plates, and you want to train a neural model on the real actual data. So no de-anonymization, no blurring, no removing of faces or anything. You want to train on the real data, but it should be done in such a secure environment so nobody can peek inside, not even Bosch. And you can verify this to any third-party regulators. And we used confidential computing to essentially build a de-identification phase where the image is split up. You can process the non-PI part separately, more efficiently with an external labeling company, and then join the image back together and train it in a secure environment. If you want to see the details of this project, it was presented at Intel Vision and Microsoft Build Conference. You will find the recordings online. But this is just to give you an idea what such new types of applications could be. So how can we know that we know what confidential computing roughly is? If we have a Kubernetes world, how can we use it? How can we use of those secure environments? I guess I don't have to show you the slide here in this conference, but just to explain this image once, this should display a Kubernetes node that has a bunch of pods, and in those pods there are a bunch of containers. And if we take a bigger picture, or zoom out a bit, if the Kubernetes world and the cloud today, you have a control plane, you have a worker nodes, which was shown before, but you also have a bunch of cloud services that are provided by the cloud providers, like storage, load balancing, managed services, and so forth. And everywhere here, as said, there are components you have to trust. And the first concept I'd like to present is, I would generalize it as confidential containers. And one flavor of confidential containers is based on Intel SGX. So you could take your application, you can package it in SGX, and package this again inside a container. There are different solutions for packaging applications into SGX. In general, you either have the choice between a library OS that basically somehow abstracts away the system interface, so you could just lift and shift your code more or less inside an SGX enclave, or you have those library-specific SDKs for Go, Ego, or for Rust, and you package your application inside an SGX enclave with those toolings, you package them in a container, and you deploy it to the cloud. From a Kubernetes node perspective, SGX is just a Linux device, exposed as a Linux device. So there are device drivers for Kubernetes for SGX. One is from Intel itself. So you need to install this device driver. You need the Intel chips in this case for your worker nodes, and then you just request for those containers, for those pods where you want to run SGX applications, you request SGX resources that are exposed by the device driver. And that's it. Then your application is running. The problem here is that lift and shift with SGX usually does not work that well. It's always a bit complicated. It's a bit tricky because it's process-based and you don't have this full system interface. So there's another approach. It's called actually called confidential containers, as a new CNCF sandbox project. And the idea here is that you borrow the concept of kata containers. Kata containers, I don't want to go into details, but essentially means for every pod you have a virtual machine, so it uses nested virtualization in most cases. And the idea actually of kata is to protect your system from the containers you're running. And confidential containers takes this concept and turns it around, so you're protecting the containers from the underlying system by creating a confidential VM per pod. And of course, if you have a confidential VM, you can deploy any container inside, and that's it. That's pretty easy lift and shift. So these are the two concepts, one taking SGX and the other building up on confidential VMs. From the bigger picture, what this means is if we have a node with the required hardware capabilities, we then can create confidential containers in our worker nodes, and our application runs securely inside. The tricky part, or what's missing, is how can we now orchestrate this, right? You see the control plane is still untrusted territory. You cannot just, let's say, if you have a secret, you can just use the Qt API server and the etcd state to store secrets inside, because they could be stolen. Similarly, the cloud services, cloud storage, anything here is not trusted. And make this a bit more concrete, going back to our Bosch project. We wanted to deploy this pipeline into the public cloud. In this case, it was Azure, and it should be just scalable like any other cloud-native application. So the first question was, how can the DevOps engineers, the CloudOps team, how can they securely provide deployment configurations for these services without trusting the Kube API server or any other control plane component? And how can we verify then each of these services has the correct identities? How can they do the remote attestation without verifying each individual instance? I mean, if you want to scale up and down one of those pipeline steps, you would manually need to verify every single one of them, and also implement this on the application layer to expose those remote attestation statements. That was the first challenge. The second challenge was then, how can one service verify the other service? Again, if service A wants to provide data to service B, it needs to be sure that this is actually running in a secure enclave, has the correct identity. And again, I don't want to solve this on the application layer. I want to have this solved on a different layer for me. And lastly, how can the car fleet or any external party verify the entire deployment without knowing the inner details of this microservice architecture? Right? Could internally change how these services interact, and I don't want the car to know about this and verify this. So the solution in this case, and it's a general concept, it was in this case implemented with the Mabran project or tool, that the idea is that you add a trusted party to the control plane, let's say, trusted controller, and this itself runs inside a secure enclave that can then be verified using remote attestation and provided with a manifest, like your usual deployment files. This manifest contains the identities of your services and how they should be configured and so forth. So when your services come up, they connect to the control plane here, to the Mabran control plane. They provide an attestation statements, they are verified, provided with credentials, secrets, their configuration, and then they can use these credentials to establish secure connections. And for the environments that support it, this can even be done then on a mutual TLS layer, like in a service mesh fashion. So the services don't even need to know how to establish secure connections. It could be done transparently for them. And lastly, then, a third party could connect again to the control plane, obtain a concise attestation statement for the entire deployment that contains a root of trust, a certificate to authenticate each of these services, connect to the pipeline, and send their data over. So from a more conceptual point of view, this concept takes confidential containers and lifts them into entire confidential deployments, so make them orchestratable and verifiable. If you go back to our bigger picture, what this means is we install a trusted party to the control plane, and this takes care of bootstrapping and creating such a confidential overlay in our deployments. And this is great, and this solved the case for Bosch. And I think it's a good concept if you want to build new types of application that build up on this confidential container concept. The problem here is it still doesn't really fit the lift and shift case, where you just want to move your workloads to the cloud. You don't want to adapt anything, change anything. You might have an on-prem Kubernetes cluster running, and you also already have this deployment. You just want to move them over and be done with it. And don't think about how you verify those services, even though the Marlboro control plane could help you there. And this last concept that is the closest to how you to lift and shift, essentially, I will call that confidential Kubernetes. So the basic idea here is that you move the entire Kubernetes node inside a confidential VM. This means all the Kubernetes components run inside this confidential VM. If you would just do that, you could call it Kubernetes with confidential VMs. And you already get that in the cloud. K8s can do that. I think GKE can also do that. They could run your managed Kubernetes cluster with confidential VMs. The problem, the control plane still is not in confidential VMs. It's not verifiable. Your nodes are not verified between each other. They're not attested. The question is how does storage work? Do I need to solve this on the application layer? Because I can't just use the regular encrypted cloud storage. It's encrypted somewhere in the back end of the cloud provider. I can't trust this encryption, even if I use some bring my own key solution, right? I don't have control over the encryption. And the difference here with confidential Kubernetes is then that you move this from that you basically extend this concept even further. You run the control plane in confidential VMs, and then you do node attestation. So every node that joins the cluster is verified using remote attestation, and then joined to the cluster, and from that point on is considered trusted. And similarly, you transparently encrypt storage that's mounted into your cluster using, for example, the CSI interface. So it's encrypted on the node level where the encryption happens inside this confidential VM context. And lastly, then you can verify this entire cluster using remote attestation. This is the confidential Kubernetes concept. Again, the difference, Kubernetes with confidential VMs to having the entire cluster here encrypted and verifiable. So the conclusion, what can confidential computing give you as a cloud-native architect or building cloud-native application? It can give you always encrypted, everything is always encrypted, runtime encrypted workloads. You can have everything verifiable, depending on your use case. If you're building new stuff or you want very fine-grained controls, you can go down the confidential containers route. You need to adapt maybe a bit. If you just want a private carve-out in the public cloud, just want to lift and shift into a runtime encrypted environment that's still verifiable, you go down the confidential Kubernetes route. So everything is verifiable. And with confidential computing, you have, compared to other privacy-preserving technologies, you have very good performance. You have slight overhead for the runtime encryption. You have slight overhead for the other encryptions that probably already happen in your cluster today, but you still have to consider them. but it's a completely different world compared to fully homomorphic encryption or other types of privacy-enhancing technology. And it's very easy integratable, right? We've seen that you just need the device drivers for SGX. You have the confidential VMs that are more or less fully transparent for you if you just go down the confidential VM route. But talking about integration, this is pretty much our mission at Edgeless. We build open source tools for these types of tasks, for bridging the gap here. We have more tools more focused on the building new types of applications, a Go SDK for lifting lifting Go applications into SGX enclaves, a control plane or orchestration tool for the confidential container concept. That's called Mabarun, and a database that runs entirely inside SGX. And on the other hand, we have the lift and shift solution that implements this confidential Kubernetes concept. It's called Constellation. It's not open source yet, but rumor has it there's some news around the corner. So you heard it here first. There might be something up in the next couple of weeks. Make sure if you're interested in that to follow the Twitter feed. And yeah, with that, I'm done. Thank you very much. And I think we have plenty of time for Q&A.
Cool. Thanks, Moritz. It's great to hear about more security implementations within our sphere. I'm a big fan of security. Cool. Yeah, we do have some questions, I believe. Because the first one is, how can remote attestation be implemented? Are there any tools that can help with that?
Right. I mean, in general, all the tools I showed you today already help you with remote attestation, right? Mabarun essentially does remote attestation for all your confidential containers and then provides you with one attestation statement. And this attestation statement can be verified in 2 steps. You first verify that it's valid. This doesn't really depend it depends a bit on the hardware technology, but it always works the same. You have some certificate that can be routed back to the hardware vendor, may it be Intel or AMD or whatever. And once you've done that, the statement basically contains the measurements of the workloads running inside those deployments and so forth. So you just need the measurements to compare them against. And these can be computed offline. So when you build your application, you get a measurement, and then you verify that against the one presented in the remote attestation statement. And with confidential Kubernetes, it's a bit different maybe. You do the same approach, you verify the attestation statement, and then in the statement, you have the entire measurement of those Kubernetes nodes. So you can see that every node you see basically the measured boot of this node. And then you see, okay, this is the benign Constellation node, and you do that. You get that for the entire cluster, and then you know the entire cluster is consisting of those benign nodes. Maybe one more thing, because we have a bit of time. There are other solutions to make this more policy-based, if you will. So there's the Azure Attestation Server that's specific to Azure, where they have a policy engine with a policy language, and then you could basically write a bit of policies that define certain actions based on remote attestation statements, basically releasing a key based on certain measurements and presented in a statement. Yeah.
Cool. How are keys managed in confidential compute?
Right. There are several keys floating around. You have those keys in the CPUs, the essential keys that do the memory encryption. They are burned in. They are just managed by the hardware provider. They are burned in the production state. You don't really have to care about them. Then there are the keys that are part, let's say, of Kubernetes or of the application. And this is then, again, application specific. Just to give you examples again, Mabarun can manage keys for you. Constellation can manage keys for you. But yeah, this is then dependent on the software implementation.
All right. I'm going to go through all the questions. I think we have more than enough time, and the audience is interested. So you said this was possible also with the current cloud providers. But for instance, Azure have complete control of the control plane. How do we get this trusted?
Yeah, it's the right question. Yeah, you don't. Currently, yeah, you could say this story has a bit of a hole there, right? You can't verify the control plane, hence you can't trust it. You have to trust it because it has a lot of control over your cluster and it has a lot of access. Eventually, they might make also encrypted, or use confidential VMs there as well, and maybe make it verifiable. But status quo is you can't, and this is why a tool like Constellation makes sense, where you close this hole.
Yeah, I mean, it's most cloud providers would not be able to do that because you give them they're the ones controlling the control plane. That's why you've got a managed system. So yeah, it's a benefits and
right, exactly.
Cool, awesome. How am I supposed to trust Intel SGX stuff after Meltdown, Spectre, etc.?
It's a good question. I guess I think it's very good that we have the research doing this, finding those side channel attacks, right, like Spectre, Meltdown, and so forth. And obviously they also affected SGX, and SGX has since then patched, or they found, or Intel worked on migrating those things. You can never be certain that there will not be another side channel, right? The only thing you can do is do more of this research, find them before other people find them, patch quickly. I guess then it's personal choice if you think that's trustworthy or not.
Yeah, there needs to be a level of trust at a point in time. Cool. How much overhead does all this encryption and verification will bring to the workloads?
Also, very good question. Mm-hmm. This again depends on the hardware a bit. SGX naturally has a bit of more overhead than the confidential VM solutions because SGX has to do these context switches if you leave the process-based secure enclave. I can't really give you SGX numbers, but with the latest, I think it was Ice Lake, they improved it by quite a bit, and you're in the I don't know, upper single digits, smaller double-digit percentages. With confidential VMs, there are some benchmarks. We did some benchmarks on the overhead of confidential Kubernetes. That was pretty decent. AMD and Azure did a benchmark on the runtime overhead, and I think they were about, in the worst case, about 9%. And with our benchmarks, we were pretty much equal with like storage encryption and network encryption to the native implementations of these in Azure and GCP. So you could say this is almost negligible at this point. Yeah.
Cool. And final one. How would Edgeless DB fit into a Kubernetes world? What security guarantees does it provide anyway? Right.
What security guarantees does it provide? It runs inside an SGX enclave. It can be verified. It can. It's runtime encrypted, of course, and it's built up on MariaDB and the RocksDB storage backend, essentially, and it has some modifications to the storage backend to hold up against the confidential computing attacker model that basically has full control over everything. We can do replay attacks and so forth. So it has an extension on the storage backend as well. How does it fit in Kubernetes? You could run it inside a Kubernetes cluster as a database. It's in the Azure Marketplace. You can also deploy it from there and then use it as a service. It's not provided as a managed service yet. Might be, though.
Cool. All right. Thank you, Moritz.
Thank you very much.